For this one, the figure shows two circular pack of coil. The smaller one with radius R2 with N2 turn, the largest one is radius R1 and N1 turn, something like the setting in the lab too, and in the same plane. Derive an expression for the mutual inductance M of this arrangement of these two coils, assuming that R1 is much larger than R2. So first of all, because we need to calculate the mutual inductance, we need to write down the magnetic flux from the coil 1 for the coil 2. I mean the magnetic flux of coil 2 due to coil 1, because actually for this case R1 is the outer one, and here we have a battery here, so there will be some current going through the outer loop, and the outer loop will generate some sort of magnetic field. And if this magnetic field is changing, so the magnetic flux go through the coil 2 will also be changing. So this will generate and induce EMF for coil 2. And here we'll with an ammeter, so that we can measure this small current going through this loop, the second loop, I mean. So for this case, the magnetic flux for coil 2 due to coil 1, we write it as phi 21 equals B1A. And actually we have M equals N2, N2 phi 21 over I1. It's something like the inductance, but we change L into M, and also the phi into phi 21, and the I is I1 because it's generated by the first loop. So we'll have N2 B1A2 over I1. And for equation 29, 26, we have BZ equals mu 0 I R square 2 R square plus C square to the 3 over 2 power at Z equals 0. Z equals 0. 0 axis is perpendicular to this plane, Z directly, something like this. So on this plane, Z is equals to 0. So we'll have B1 equals to B0 times N, of course. At that time, we don't have many coil. We derive this equation for one coil. So actually, we'll have B1 equals to N1 times B V0 for this case. So I can still write it here, N1 times mu 0 I1 over 2R1. Okay, so this R will become R1. This R will become R1. So we have R squared here, and this R also become R1, and Z is 0. So this is R squared to the 3/2 power. So the two of the power cancel, so only R1 is here, and it will be something like this. So I add another page. Okay. So we have M. So we have M equals N1 mu 0 I 2/R1 times N2 A2 over I1. Let me go back a bit. So we substitute this one into here. So we have N2 A2 over I1, N2 A2 over I1, and this is the B1. And also A2 equals pi R2 squared, because it is a circle. So finally we'll get M equals mu 0 N1 N2 pi R2 squared over 2R1. Okay, so that's the answer for question A. This is pi. And for question B, what is the value of M for N1 equals N2 equals 1,200 turns? R2 is 1.1 centimeter, R1 is 15 centimeters. So we have M equals pi mu 0 N1 N2 R2 square over 2R1, and we substitute all the numbers. Mu is 4 pi times 10 to minus 7. N1 and N2 are also 1,200. And R2 is 1.1 centimeter, so 0.011 square, and over 2 times 0.15. So we'll get mutual inductance equals to 2.29 millihenry, which is quite large. So any question for this one? direction. Okay, move on. So for this one, one long coaxial cable consists of two thin wall concentric conducting cylinders with radii A and radii B. So this is coaxial cable, which means two layers, one inner layer and outer layer. This is A, this is B. So the inner cylinder carries static current I going maybe into or outside the page, and the outer cylinder provide a return path for the current. So the current for these two layers go in opposite direction. One go in and another go out. The current set up a magnetic field between the two cylinders. Calculate the energy stored in the magnetic field for the length L of the cable. So we use the Ampere's law. We use the Ampere's law. B ES equals mu 0 I. And the Ampere's loop is, I think, this one. So for this circle, we have B times 2 pi r. This is the line integral for this loop. And so if it is uniform, it's something like the magnetic field times the circumference of this circle. So it is equals to mu 0 I. So we'll have B equals mu 0 I 2 pi r. And the magnetic and the energy stored in the magnetic field is something like this. This is small u of B equals B squared over 2 mu 0. And we substitute B into this equation, so we'll have mu 0 I squared over 8 pi squared r squared. So we can write dUB. dUB will be UB is the energy density times the infinitesimal volume for that volume. So we'll have mu 0 I square 8 pi square over r square dV. So this is the cylindrical coordinate. So dV will be r dr d theta dz. This one is this one. Okay, you can regard it as a polar coordinate plus another z-axis. So this is the cylindrical coordinate. I also need to add a page here. So we can write it as UB equals the integration of DUB. So the constant move out mu 0 I square over 8 pi square, and we have here we have R square and R, so one of the R cancel each other. So we have R dr, and it is integrate from A to B, because the magnetic field should be between these two layers. So we integrate from A to B. Okay. Oh, yeah. And theta, of course, integrate from 0 to 2 pi. And z is integrate from 0 to small l, because it tells you for length L of the cable. So the z-axis is from 0 to small l. So this integration is easy. Mu 0 I squared over 8 pi squared. This one is log b over a times 2 pi times l. So we can write it as mu 0 I square L over 4 pi log b over a. And this is the answer. Any question regarding to this one? Okay, so move on. What is the store energy? Also, okay, it's just substitute all the number in it, per unit length. So actually, what we really need to calculate is something like UB over L, which is mu 0 I square over 4 pi times ln b over a. So mu 0 is 4 pi times 10 to minus 7, so the 4 pi can be cancelled. So it's only 10 to minus 7. I is 2.7 ampere. And ln 3.5 over 1.2. So the answer is 7.8 times 10 to minus 7 joule over meter. Okay, so for the next one, two parallel loops of wire have a common axis. So which means these two circles on the planes are parallel to each other, and if you draw a line perpendicular to these two planes, and this line will go through the center of these two circles, which means they have the same common axis, which means they are concentric, and then you move it upward, something like that. So the smaller loop with radius small r is above the larger loop by distance. X is much larger than capital R. Consequently, the magnetic field due to the counterclockwise current I in the larger loop is near uniform throughout the smaller loop. Suppose that X is increasing at the constant rate V equals dx dt. So this is moving, and it also assumes X is much larger than R, so that it can assume the magnetic field across the smaller loop is almost uniform. So it asks you find an expression for the magnetic flux through the area for the smaller loop as a function of X. Okay. So for equation 2924, we have like this. So in this case, we will try to fix the notation. So actually, B is mu 0 over 2 pi, and mu is actually I times pi r square, x3 over, this is x in this case. At that time that is z, but here it is x, so we change the variable, and it is in x direction, so that we write it like this. So for the midterm exam, actually the mu is something like this, or yeah, it's actually like this. Actually, you can find it in the equation table. So phi b will be approximately b times a, because it tells you it is nearly uniform. So, but it doesn't really matter. So we can write it like this. I times pi r square over x cubed, and then a is pi r square for the smaller coil. Okay, so it is something like mu 0 I pi. It depends on how you arrange the order of the variable, but it doesn't really matter. Something like this. You just cancel one of the pi, and you have 2x cubed at the bottom, and pi mu 0 I. Oh, this is not I. Oh, this is I. This is not I, not I1. So we have pi mu 0 I r square, capital R square on the top. So this is the answer of question A. And now so for the smaller loop, find an equation for the induced EMF, What? Oh, you just ignore this one. Okay. So find the expression for the induced EMF. For the previous question, we already have phi b. So actually, according to Faraday's law, we can write the induced EMF equals to the time derivative of phi b. So we can simply write it like minus pi mu 0 I r square over 2, and of course we need to take the derivative of time with respect to 1 over x cubed, because all the terms are constant with respect to time. Only variable are x, because it tells you that the loop is moving. The loop is moving with a constant rate. So we need to consider the derivative of this term. So we have pi mu 0 I r square over 2. So the derivative of this term is you can write it as x2 minus 3. x2 minus 3. So it is minus 3 over x to the 4th power, and don't forget the chain rule, dx dt. So finally, the answer will be 2/3 mu 0 I r square over x to the 4th power times v, and this is the answer for B. This is the answer for B. And for C, the direction of the induced current. So actually, we need to consider it like this. So for the lower loop, the current is counterclockwise. So use the right-hand rule. The magnetic field is pointing upward, and actually we can what we can derive here is E is positive. E is positive. So according to right-hand rule, the EMF is also counterclockwise. So for C, the EMF is counterclockwise.